Hi everyone. First, I'd like to thank Facebook for inviting us here. My name is Diogo Mónica, and this is my colleague Nathan McCauley, and we work in the Square security team. Today, and before I go into my talk, let me just go a little bit over a background of why we're doing this and why this talk. So, as Joe said in the beginning of today, it's actually been an interesting year for information security. 2013 was a really interesting year for us. I think for Square, there were two things that were particularly interesting. The first one was that Snowden leaks really validated our attacker model. So since 2011, we've been doing mutual TLS between data centers. We've been doing mutual TLS between applications. We've been even doing mutual authenticated SSL between localhost and itself. So it really validated our attacker model on that end. The second thing that was really interesting for us was the very high number of high-impact leaks in cases of people being compromised. So let me share this with you. At Square, we have this small tradition. Every time there's a leak, a high-impact leak outside, basically we meet informally or formally in a room, and we go over the details. What happened? Why did it happen? And the most important thing that we actually do is, ask the question, would this happen to us? Would this happen in our infrastructure? What currently in our infrastructure would prevent this from happening, and if anything at all? So it was actually while we were in the process of doing this and looking at these things that we realized that there were some things that while architecting our infrastructure since 2011, since 2009, we were doing the same conscious decisions over and over again. The talk today about crypto anchoring is really going to delve into a particular aspect that we've discovered that we're doing consistently in our architecture that allows us to protect against offline attacks. Perfect. So in essence, what is an offline attack? So an offline attack starts with an attacker compromising company X, right? So there's a company, the attacker compromised this company somehow. The second step is really the attacker downloads the contents. So it downloads the contents to his laptop, downloads the contents to his home server, downloads the contents to Amazon EC2, something like that. And then the third step really is that the attacker has fun at home. So it has the contents, it has everything it needs. It can just go ahead and have fun by itself at home. So a few examples of offline attacks. The one canonical case really is password dumps, right? Last year, we've seen a bunch of those. We've seen passwords hashed with MD5, no salt. That was great. We've seen passwords SHA-1, no salt. We've seen passwords encrypted with 3 DES in ECB mode, which was amazing. So that was a new thing for us. But even cases where we're doing the right thing, we're using bcrypt, we're using scrypt, you're using whatever rocks your boat, PBKDF2. Even cases like that, you have to realize that a password dump, something that gets downloaded to attacker's computer, is still prone to being brute forced individual passwords, right? You can still brute force these passwords offline. So there's still an offline attack possible. Another class of examples of offline attacks is when an attacker really steals a private key. So there's some private key. Usually the host that operates on the data is also the same host that has the key to decrypt this data. And this means that if the host has both the data and the key, the attacker compromises the host, takes everything offline, and now it can decrypt the content offline. And more than that, it can actually, if it's, for example, a cookie and it's an HMAC key, or if it's a private key and he's able to sign API requests, now the attacker can actually, in an isolated form, create valid requests with which it can interact with certain specific parts of our infrastructure without triggering the whole thing. So signing cookies and just replaying that, or signing a certificate for itself and doing a man in the middle. So it becomes really an isolated attack if they're able to do this. So this is also a common example of something that really allows an offline attack. So now the question really is, OK, offline attacks are bad. I got it. How do we turn an offline attack into an online attack? So how do we do this? So I can't really stand here and say that we can mitigate number one. I cannot say that I can 100% of the time make sure an attacker does not compromise in company X. It's going to happen. Somebody's going to be compromised. Some host's going to be compromised. Whether it's important or not, it's a different story. But we're going to be compromised eventually. The attacker can download the contents. Well, there's really also nothing that we can do about this. If the attacker has access to the contents, if it has access to the bits, it can replicate them, even if it's just by copy-pasting the terminal, right? It can just get the data outside of the content that it was and just have it at home. What we can do, though, is that we do not allow the attacker to have fun at home. So we're going to make sure that the attacker is going to play on our grounds. The attacker is going to have fun inside of our data center. And now the question is, why? Why would you do this? And the answer actually turns out it's pretty obvious. So if the attacker is not playing at home, if the attacker is playing in your data center, this means that your intrusion detection systems are going to be there. You are going to be able to log every action that is going to do inside of your data center. You are going to have load monitoring. So if it somehow trips some load issue, you are going to know about it and you're going to be alerted. You're going to have alerting systems, and you're going to have a series of things that really are going to make the attacker be like a bull in a china shop. He's going to break a vase eventually. If he's inside of your data center, there's going to be some vase that's going to fall down, some very important vase, and it's going to crash on the floor, and you're going to realize it because you're going to be paged at 3 a.m. So that's great, right? We're going to detect it. So the point really here is make the attacker work in an adversarial environment. Do not let him take the data home. Do not let him have fun at home. So for a very simple example, let's take the example of a simple password or a simple web service that has a front end and it has a back end, which is a database. In this case, is a Rails, Ruby on Rails front end, and the database is a MySQL backend server. And in this case, we actually did the right thing, and we stored our users' passwords with a bcrypt hash. Cool. So imagine a compromise of the front-end server. So somebody comes along, uses a Rails RCE, and it has the front-end server. So if it has a front-end server, this really means, in this particular case, that it also has unlimited access to the database, unlimited queries, unlimited dumps. So the attacker can just take all the data and go home with it. So what we really want here, what we really, really want is we want a way of anchoring this data. We want a way of making sure that that backend server's data does not leave our data center. So we came up with something that we call a crypto anchor. So a crypto anchor essentially is a functionality that is going to bind your data to a secure environment. And we're going to do this through the use of cryptography. So it's an anchor. We use cryptography. It's a crypto anchor. We're really proud of this name. The way the cryptography is going to work, or the way this anchor is going to work, is really going to be, it's going to be a shim, or it's going to be something that stands in front of your data and behind your front-end service, and it's going to ensure that the attacker cannot take the data away. Or even if he can, it cannot use that data while he's away. So we're going to turn this into an online attack. Concrete example. So imagine that instead of the anchor, or instead of not having anything between the front end and the back end, now we have something that we call the auth service. So there's an authentication service. In this case, it's built in Java. And instead of actually having our hashes being bcrypt, we have some keyed hash function. It could be something that also provides the bcrypt functionalities, but it's also appended with a key. Also, interestingly, our authentication service is the only host that has this key. So what happens now? Somebody compromises the Rails front end on your left, and they have access to this API that the authentication service that provides to do authentication, right? They do not have direct database access. They do not have access directly to the database. They can just request authentication mechanisms. They do not have access to the database. If they do want to take this offline, and if they do want to take the data, they have somehow to get the data from the database, either compromising directly the database or compromising it some other way, stealing from backups. But they do have to do one thing, which is they have to go to our authentication service and steal that key. So this is our example number one. The first one, we didn't have anything. Number two, we have an authentication service that is going to work as a crypto anchor, and it's going to have our hashing key there. The third example is really just a little bit of a twist over this one. And the only difference between the previous one and this is that our key actually now lives in a hardware security module. So hardware security modules are these kind of cool things that we assume are unbreakable. And once we generate a key inside of them, they never come out. We can make operations on these keys, but we can't really extract the key. So now let's look at probability of compromises. We have these three examples. We have the example in which we have a front end and a database. We have an example in which we have the front end, an authentication service with a key in memory or with a key in disk, and the back end. And we have the third one, which is the same thing, but with an HSM. So given that the probability of a Rails vulnerability is actually independent of time, and it's 1 at all times, I'll give you that one for free. I know, it's really bad. Given that that probability is 1, we're not really going to care about that, but we are going to care about the fact that probability of pivoting, well, it does tend to 1, but it gives us a timeline. So it is not 1 immediately like a Rails RCE. It actually gives us some time to detect and to do something about it. So let's look at the three examples again and kind of like break them down on what I'm actually saying here. Scenario number one. Scenario number one, the probability of taking the database offline is the probability of Rails being compromised, which is 1. So P of database offline equals 1. Interestingly, the number of hosts that you have to compromise is just one. And I created something called detectable events. And by this, I mean events in your infrastructure that you are bound to detect somehow. In either an IDS or in some log or some mechanism that you have in your company, you're bound to detect these events because they either match some signature of a known attack or they just match some heuristic that you have in your infrastructure. So detectable events of scenario number one is just one. However, look what happens once we throw in our anchor, our crypto anchor into the mix and actually create an authentication service. So scenario number two, the probability of database offline is the probability of RCE being compromised, right, which is 1, multiplied by the probability of pivoting. So we actually were able to significantly decrease the probability of having our database offline by just creating middleman service, a crypto anchor right there in the middle. We were able to leave the probability and decrease the probability significantly. But more interestingly than this is that the number of hosts that have to be compromised now is 2. And the number of detectable events actually grows a lot. We still have the ability to detect the Rails RCE, right? It's still the same source of compromise in this example. But now note that while in a front-end service, you are constantly being bombarded by port scans, by application attempts to do SQL injections or cross-site scripting or anything, to the point where we actually, in practice, ignore those things. It's just a statistic. If we don't have those things, something is wrong, which is kind of interesting. But they're always happening. However, inside of our infrastructure, that is not true. So now there's going to be another step that an attacker has to do, which is host and network reconnaissance. So once he gets to our RCE front-end server, it now has to do reconnaissance and port scans and actually understand what our infrastructure is actually doing on the inside. So while on a front end, scenario number 1, a port scan means no information. On scenario number 2, a port scan is actually an alertable event. If there's one of my front-end servers doing a sweep of all TCP ports inside of my system, I want to know. That is interesting. I want to know. Not only that, he's going to do everything that he would do from the outside and we would ignore. He's going to try XSS. He's going to try XSS would not be useful, but SQL injection, remote code execution. He's going to try a bunch of exploit. He's going to be, again, a bull in a china shop, trying to compromise. Plus, we still have the ability of detecting the actual attack that succeeds, right? The pivoting itself, not only the reconnaissance, but the attacks themselves are another thing that we can detect. So we just turned something that we don't have a lot of information, we don't have a lot of ability to detect, detectable events 1, to something that we actually have a lot of probability of detecting because we have a lot of information and a lot of data bringing up. Scenario number 3 is exactly the same thing as scenario number 2, except that the probability of taking offline is actually turned to 0 because we now have an HSM. Cool. So particular examples that we're going to do at Square, I'm going to give the word to my colleague, Nathan McCauley. He's going to walk through some examples that we've done this and that we've applied the concept of crypto anchor at Square for some particular events. Thanks.
Yep. So we're going to go through 4 examples. They're going to be varying degrees of real and idealistic. But some of these are actually ones that we've deployed. Some of the ones are ones that we're thinking about right now. We'll go through a service setup without the crypto anchor and then add the crypto anchor to kind of illustrate the point of what advantages we get out of adding crypto anchors. First one we talk about is we've got a problem where we need to make encrypted card readers. And these encrypted card readers need per device symmetric AES keys. We have to distribute these all out into the world, and we want a way to generate and keep track of these so that when transactions come back in, we can decrypt and figure out what the data was associated with that transaction. So the questions that come before us is, how do we generate these keys? And then how do we store them within our infrastructure? So a naive or meh solution you might come up with is just randomly generate the keys and store an association, ID to key, in some database. So this looks good. It's going to work. You got to do a database call when you do a transaction. But other than that, it looks good. The problem here is that a database compromise leaks all of our keys, and we're looking at a reader recall, which would be very expensive and very sad for everyone involved. So how can we add a crypto anchor into this system? One way we can do it is we have a key generation service, and the keys for each device are based on a key derivation function. And if we use a keyed key derivation function, such as HMAC, then each reader is just an HMAC call, and we've got a key that we can then decide to protect. There's no database that we can lose and allow someone to go offline with. And optionally, like in the other ones, we can put in a hardware security module to put that key in. So I'm feeling pretty good about this. There's no way to exfiltrate all of our keys because they're all HSM derived. Let's consider another service. Fidelius is our secret keeping service. It's our tokenization server, essentially. You give it some stable data, and it gives you a stable identifier to go refer to it later. So this is another one where we need to store a bunch of data, and we need to have a mapping between token to encrypted data. So we need some sort of a mapping system there. And we also need a way to store the data encrypted. So our first solution is just put this in the database hanging off of the payment service. As credit cards come in, payment service encrypts them, puts them in their database with some key that the payment service has. And you assign some random token. So this works. The payment service is responsible for tokenizing the credit cards. But we can do better. The tokenization service could be introduced, and it can be responsible for key management and for token generation. The token generation can, once again, it could be based off an HMAC of the plaintext data, and that HMAC key can be protected. And then the encryption and decryption keys, whatever scheme you want to use there, can be introduced inside of the tokenization service itself. Let's consider another one. Multipass is kind of our authentication service. Our goal here is to authenticate an API call all the way through as it passes through many services, possibly a dozen services as part of one API request. So how do you know that it was issued by the application that you wanted associated with the user? And how do you ensure granular access control for the middleware services? The default naive approach here is the user's device passes up a cookie goes into the auth service. The auth service says, okay, cool, everything's cool, and then responds to the front-end service, sure, do whatever you want. Front-end server then prepares the rest of the request. The request travels through the infrastructure, and basically any of the middleware services, for example, this one in the middle, or any of the other downstreams, are just given carte blanche access to each other's data. So there's no real way to add an authentication system here. So the way you improve this is something that looks pretty similar to Kerberos. You send up the cookie, the authorization service responds with a short-lived token that gets passed along with the rest of the RPCs. This token is then validated at every step, and access control decisions are allowed to be made on that. And what you can do here is, in the auth service, you need to sign this short-lived token. Signing is a crypto operation. So we've got a crypto anchor in our authorization service. Finally, a piece of general infrastructure is just a HSM front end. Do you want to have an HSM that might take hundreds of requests a second? It needs to decrypt data and then return it to you. The team this morning talked about using Bletchley in our Hadoop infrastructure. So the question is, where does the decryption key live, and who has the permission to do the decryptions? Again, a very simple model is one where maybe the payment service itself could decrypt the keys or decrypt the data coming from the transactions. And if you've got the P, you've got the permissions. And key compromise here is quite easy, so we'd like to improve this. So you introduce Bletchley, a decryption service that becomes the crypto anchor for this system. And the authentication and authorization are on a per application basis. And Bletchley ends up being interesting. If you build an HSM service within your infrastructure, you can allow a bunch more crypto anchors just by having that primitive available. So pass it over to Diogo to talk about some generic conclusions.
So far we've seen that crypto anchors can be used basically generic to basically turn any piece of infrastructure that you want into an online attack. So our arguments here in favor of a solution like this and an architecture where you think about putting these things and like compose your architecture with things like this is that first one, pivoting inside of a data center is not trivial. And not only it's not trivial, it's going to be a lot easier to detect than a front-end compromise. They're going to be operating inside of your data center. They're going to be playing by your rules. They're going to be tripping on your alerts, and they're going to be breaking all of your stuff. Another thing is that more services really gives us better detection capabilities or better chances to detect these attacks. And one of the reasons for that is that you can really tune in and create a per service baseline of service that you're expecting. If you have an authentication service, you can see what the pattern of authentications is. If you have a key generation service, you know how many keys usually are generated per day. If somebody compromises your data center or your front end and starts basically brute forcing and trying to generate all the keys, you'll know. There's going to be a spike, there's going to be an alert. And this is opposed to just stealing the database and running away with it. So we have more capability and we have more time and we have more ability to actually detect and protect against an attack like this. Another thing that that in general, it's an argument, is that if you do split these core functionalities of security into individual services, like we've been composing, it really gives you better application reuse. As Nathan mentioned, Bletchley is a great example of both a crypto anchor that can be used to turn an offline flow to an online application flow, but it also can be shared throughout all of our infrastructure through several things. For example, enabling offline payments, decrypting credit cards that come from our partners, all of these different things that we can do based on this core fundamental piece of infrastructure. It also allows us to do better segmentation. If you have different services, and if one service is called the decryption service, you're not going to put the decryption service inside of the same network zone or inside of the same security zone as the front-end service. You're going to put it behind a different firewall. You're going to put it behind a different IDS. You're going to put more concrete rules around what it's doing, what it's not doing. You're going to have more tightened up logs. You can actually monitor it individually instead of monitoring the whole thing and just seeing a bunch of data. So this is really useful for us. And this leads to the better monitoring, right? So we have individual services, people that did these individual services. They understand what the baselines are. They understand what normal mode of operation means. If there's a not normal mode or weird mode of operation, that's going to be an alertable event. That's going to be something that we're going to be knowing about. And that's going to be something that we're going to be looking into. So in terms of general principles, if I could wrap something up real quickly so you guys can actually just apply this to your architectures and to designs of your architectures. Really, services that store data should not be directly accessible to front ends. This seems to be against what everybody's been doing for the past 10 years, but it's something that is logical and makes a lot of sense. So the reason for this is that they will get popped. If you're using Ruby on Rails, we've seen that the probability of getting popped is 1 and does not vary against time. And if you use PHP, even worse. But if you, even if you use Java or something like that, there's going to be an opportunity if that actually happens. The other thing is that we should really be splitting core security functionality into independent services. Twofold, 2 reasons for this. The first one is you enable crypto anchors. Now you have the ability of actually turning these things into an online attack. So you're consciously segregating these services into something that says, okay, I know that this service has these requirements, and I know that this service is going to bring me this thing, and the compromise of this key is the most important thing. So you enable crypto anchors, and you're able to bring the online flows, or you're going to be able to bring your application flows online. Finally, you can also host services, and you should also host services in different security zones. Do that. Do different network services, network security zones, do different IDSs, do different environments where you know that they are different from a front-end environment, they are different from just a normal database. A decryption service should not be operating on the same zone as other things that do not make sense or do not have the same data or do not have the same permissions.
So one kind of idea that this term crypto anchors brings up is that I'm going to sync my company with HSM costs. It doesn't have to be like that. We also thought of different terms for this, such as cyber tethering or cryptanglement, but we we abandoned those. So the anchor idea remains, but it doesn't have to be that you store the data in the HSMs. The HSMs are an improvement. For us, we actually have gone in a lot on HSMs, but it does actually help just to have the keys separated on a different service. You have some different level of control, be it network segmentation, as Diogo talked about, or different code running the service. Kind of, you can get some win there without a lot of complexity. For us, the HSMs ended up being really great. In the case of Searle, we've got an HMAC key. Put the HMAC key in the HSM, it's not leaving our infrastructure at all. Fidelius, the symmetric encryption keys for storing credit cards or other really sensitive data, needs to be tokenized. Stored in the HSM, there's no way to get that data out of our infrastructure unless you get the keys out of the HSM, which is not happening. Multipass, the signing key for the assertion that's going through the infrastructure, it's again, can be stored inside the HSM. And Bletchley, sort of like providing HSM infrastructure that anyone can use. I think the talk earlier about data deletion is really interesting because one thing you mentioned is if you have the pithiest way of writing the code, your code virally wins. So simple interfaces around crypto primitives and online services that do encryption really help you a lot.
So as a conclusion, we really have been over and hammering the message over and over again, and I just wanted to leave you with the idea of anchoring. I really like crypt entanglement, but I mean, I was outvoted on this decision. So you really should be building crypto services and crypto anchors in your architecture. And very good examples are the things that we just mentioned. So authentication services are great places to actually make sure that they're segregating their own service and they bring the flows online. Tokenization services, great spots for you to encrypt the data with a key that is inside of an HSM or some external service that actually allows you to not compromise both the keys and the data simultaneously. Decryption services, we've been hammering this message over and over again, but it's been interesting that Bletchley has been used over and over and over again. Every single architecture discussion that we've had, Bletchley somehow has the ability, this decryption magical service, has the ability of coming on and saving the day because it gives us some amazing property just because it exists. So by having these things, and by having these building blocks, we've been able to make a lot better architectural decisions instead of saying, okay, we should do this, but we're only going to be doing this because we don't have this component. So really build out the components and segregate them. Finally, key generation service, for our particular case, generating keys for our readers. Maybe you don't have this particular issue, but I'm sure you can think of a way that it would be useful for you to generate keys and a way that it would be useful for you to have a different service to making sure that those keys do not get leaked to the outside. So finally, really, it's really important to compose your application flows with one or more crypto anchors. If somebody comes in, when they come in. If not, but when they come in, they will not be able to play at home. They will have to play in your rules in your data center. Thank you very much. That was our talk. Feel free to ask any questions.
Again, great talk. Thanks.
Thank you.
My name is Ray Yan. I'm from Box.com. It's good to be reminded that PHP has a probability of being compromised, bigger than 1%. We do use PHP, by the way. So my question is, this is a lot of information. I'm a bit slow to digest. It takes a while. But I agree. I get it. Your principle is good. I get it. One thing I want to understand it better is a better example of how you pivot. The example is that what I'm looking for is, let's say if an attacker gets a key which is stored in the database somehow, then I'm still not quite following how that key cannot be used offline, right? Even with that key service in place.
Yep.
So a good example, I'm sorry, Nathan, feel free to add to this, but very good example, a very concrete example is imagine authentication service, right?
Sure.
Or a cookie signing service, right?
Yep.
If an attacker compromises your infrastructure and he steals the key that you use to sign cookies, the attacker goes home and signs cookies.
Yep.
Now imagine that I put that in a service that is my cookie signing service. Now the attacker, to sign cookies, it has to have a connection to your data center. It has to be online. It has to be presently on your data center, hammering the service that signs cookies to ask for new cookies to do all kinds of mischief.
Yep.
I see. That's a good example. So if I understand you correctly, having the keys that's stored in the database is just part of the secret, right? So it has to be combined with the secret issued by your key service in order to make the information work somehow.
Yes.
Yeah, I think there's that. They have to use the service that's able to, for example, mint cookies.
Yeah.
But the interface that you get to that service is give it a blob and returns a signed blob, or returns a cookie based on a password and username. They don't get access to the key unless they're able to pivot onto that second service. If they're able to pivot onto that second service, then they have, for example, if the key is in memory in the PHP, Java, whatever process it is, then they can get it. So the additional mechanism you can do there, if you want to be more paranoid, is put that key inside an HSM. Now the HSM is the only thing that's able to do that operation, and the key is not going to leave your infrastructure.
Oh, good. Yeah, thanks. The second question is, how do you, the HSM is great, but does it have the potential of becoming a bottleneck, a single point of failure? And if so, how do you address that? How do you provide additional redundancy?
It's a hardware failure, just like databases can fall over or hosts and disks can die, and you need to build redundancy in the same way. So you got many HSMs on many hosts.
So and to this point, I mean, Bletchley is exactly that. Bletchley was a recognition of we cannot just put an HSM inside of each host that we want to have the capability of signing something or decrypting something. So what we did was, okay, let's get a bunch of hosts. Let's get a bunch of HSMs. Let's put all the HSMs in these hosts, and then let's ignore that they have HSMs and call it Bletchley and just have an API. If we need to scale Bletchley, then we scale Bletchley. We add more hosts with more HSMs. But it can be stored in one service and it can be decoupled that way. You can think of scaling Bletchley, not necessarily scaling the HSMs. Also, these things are super parallelizable, right? You can have the same keys in 1,000 HSMs or 10,000 HSMs, and they can all simultaneously sign these things. Obviously, you don't want to have 10,000 HSMs because no company in the world has money for 10,000 HSMs. Sure. But it doesn't matter. Even if you just have 10, you can have parallelizing and you can have the power of having same key over and over again and just having scaling like that, parallel scaling.
Great. Thanks.
You're welcome.
I would add that these guys have given a talk just on Bletchley. The slides for that are online, and it's worth checking out if you care about HSMs. Anyone else?
I've got a question. Wondering if you guys.
Oh, sorry.
If you guys do anything in particular for logging to make sure that an attacker doesn't get some type of transitive access to logging and erasing records of what they've done. Specifically, I guess the question is around the HSMs and if you do anything specific with the logging for them.
So I think what you're trying to get at is, did we put something inside of the SE module that guarantees that there's some logging being spewed out by an HSM with cryptographic guarantees? Yes. The answer to that is no. However, there's a bunch of things that you can do, right? There's a bunch of services. I mean, everybody does the same thing. You have a remote logging server. The logging event is generated very fast, and it's sent out, and nobody can. It's write-only, right? So once you write the log, you can't do anything about it. And the point is that the attacker cannot compromise the logs before he compromises the host, so at least you'll have the logs of the host compromised itself. It would be a great idea if we got to the point where the SE module actually generates the events and writes them in a cryptographically sound way, but we've never gotten to that point, no. Other questions? One right there.
From a practicality standpoint, you guys are Square. You got a really great leadership team like Jack Dorsey. So you can say, I want to do this online thing. But realistically speaking, for the rest of us that don't process credit cards and aren't a type 1, I mean, what is some advice? Because you go to any developer and they're like, yeah, I'll get right on that. When they look at this very complicated system.
The first answer is do it yourself, which is to say, build a team and, constrained by whatever resources you have, build a team that can write and develop code, and then deploy these things and write reasonable interfaces to them, and they will get used. If it's easy, especially if it's the easiest thing possible, it will get used.
So, and I mean, you're totally right. Being a payments company, we do have like the flag, like we're not dealing with likes or thumbs up. I'm kidding, just kidding. We are actually dealing with money, we're moving credit cards, no offense meant. We're moving credit cards, and that means that we have all of this power, and sometimes we get drunk with power. Let's do all of these crazy things. And we have all of this power, like, oh, you can buy this, and no expense is too much to actually have this data, making sure that we put in SE the modules and the logs, and everything is cryptographically sound, and we can do a proof, and we publish a paper of how Square is provably secure, which is not going to happen, but it's hard, right? At the end of the day, I feel like the way that you can sell this really easily is you're building an SOA. You're building a service-oriented architecture. So when it comes to the decision of how are we going to authenticate, the front end communicates with the database, you're like, no, wait, we could do this as a service, we could split this as a service, and then obviously you add your protocol with the HMAC key or something that guarantees that it is a crypto anchor. And you say that I can scale it independently, I can have different code bases, I have a smaller code base, I only have to care about the service, I can have better monitoring. So you always sell it on the SOA point of view, which is necessarily what it is. At the end of the day, this is an SOA perspective on security where you make sure that there's a cryptographic guarantee that that service cannot be taken off of the flow. Because the moment that service gets taken off, the key gets taken off, and everybody comes to a halt. Everybody stops, and nothing operates. So in that sense, I would say that you could try to sell it like that. It's an SOA. We have a lot of advantages of SOA for the past 20 years that everybody agrees. And even if you're trying to sell to upper management, they know the word SOA. They do not know the word crypto anchor. And even if they don't care about security, they care about scalability. So.
Hey, Amanda from Facebook Security. I'm curious about what's your take on using things like crypto anchor with when you're dealing with. So my point is you can assume some sort of overhead when you're doing these crypto anchors because the data is really worth it. But what if you have to deal with the great amounts of data as we do, for example, right? So it's fine if you put a database, but what if you have to deal with 100 memcache servers and, 50 databases and like several things in a transaction? There are latencies involved, and there are many other things in that. And if you start caching keys, then it doesn't make any sense to do like all these complicated things. So what's your take on?
Yeah, I think to some degree this story is being written right now at Square. With the talk this morning, we talked about how we're doing encrypted data at rest in Hadoop. They have a lot of trade-offs that they're dealing with. So figuring out what the right level of trade-offs is it's engineering at its heart. I think one thing to consider is that for example, specifically for the caching case, it could be okay to cache the key somewhere else if the server that is dealing with that data is already going to get all the clear text data. So if that server has all the clear text data that's protected under that key, then the key isn't worth any more than the data. It's protecting the same amount of thing. So some kind of hybrid models like they're using, like they described this morning, could possibly make sense. And it was like a one-time checkout that allowed you to do mass decryption, for example.
And this was on the
Anything else
talk.
to add? Yeah.
This was on the talk this morning. So if you could have a key, you could cache a key that, it's not the key is going to be local, but it's going to only operate for a certain amount of time, right? So you can minimize the risk of exposure. So think of a key that only lasts for 2 hours. The attacker compromises that key, it goes home, it can work at home for 2 hours. Yeah. And then it has to come back, get another key, and go back home 2 hours. So it's not an online attack necessarily because it does not have to constantly be requesting to the service, but it is something that is weird, right? It is something if an attacker has to ask for a key every 2 hours and the system would not necessarily want the key every 2 hours, then it would be something that we'd be able to detect. But definitely you get into the gray area of we haven't had issues that are at a scale where we had to worry about it necessarily. We do have a lot of transactions per second, but not at, we don't have 100 memcache servers, thank God. It's still being written, like Nathan said. Maybe when we get to that point, we'll figure out like a good term, a middle term. We have not have to deal with that.
Thank you.
Welcome.
Hi, Kevin from Apple. Just a quick question. If you could elaborate a little bit more, you started answering my question as far as what you do when keys do get compromised and how that fits into your model.
Okay, so is the assumption here that somebody can break an HSM? Okay, fair. Okay. To be honest, the way that I think about it is maybe coming from the theoretical model. Once I put a key inside of an HSM, I really don't I really, in my head, when I'm doing architecture, I really think and I say, okay, this key cannot be compromised. However, historically in our architecture, we do have short-lived keys for mostly everything. So it is part of our DNA to create very short-lived keys and basically create services that are constantly renewing their keys. Even for our mutual TLS infrastructure, part of our goal is to have keys that live for an hour, 2 hours. And the keys are constantly being renewed, so if a key gets compromised, it goes away. So I guess the answer to that specific thing is short-lived keys, key generation, constant key generation, and a very short period of lifetime for keys.
Yep. A lot of it ends up with application-specific requirements. So for example, for our internal TLS certificates, we can issue new ones and then decide to revoke or put in the OCSP responder if we wanted, although we don't like doing that very much. For example, if some of our keys for the devices, we discovered that they were being logged somehow, for example, we can blacklist those readers so that no longer transactions are able to happen. So it's it ends up being specific to which needs, but you do want to have some plan ahead of time so that you don't end up in a situation where you have no recourse.
And even for our decryption service, we do have very short-lived keys. So sometimes we have we have to encrypt these things for this duration of time, and then when the application actually requests a key to the decryption service, the decryption service issues a key, and then when the application is done, it actually asks for the deletion, secure deletion of the key, and all the data that it is having encrypted with it just magically is turned to trash. So we do have that built in. Our solution to key revocation is very short-lived keys.
Hi.
I'm sorry, right there.
On your slides about Bletchley on SlideShare, it says the cross data center story is sad. Can you expand on that?
Wow. It's no longer sad. So you probably saw Cedric give a talk this morning. He fixed the problem.
Yeah. So basically, our data center story, the problem with that is really syncing between data centers and dealing with just partitions in general was hard. And we definitely got a way of basically we use feeds to make sure that the keys that are being produced in one data center are synced to the other data centers, which is what we're doing for everything else in our infrastructure. At the time where we built Bletchley, or when we built Bletchley, it was not something that we don't have enough keys that are across data center that have it's not real time, right? The keys are not shared real time, so we had a lot of window to actually sync them. So it wasn't really a good story because we didn't invest any effort into it. But then Cedric joined the team and he realized that, no, by the way, we're gonna have to go multi-data center with this. This actually has to be a solution. Let's use what we're using for everything else, including credit cards and payments and all of the rest of our infrastructure. And now we're using feeds, so now it's a happy story again. Now Bletchley has no issues. Perfect software. Other questions? I don't want to be kicked out of the stage. 2 more minutes. Nothing? Go ahead.
So what is the latency? How quickly can keys be synced among multiple data?
So for syncing, I believe we're going to pre-sync. So Bletchley maintains a cache of keys and then pre-syncs them before they're assigned. So it's as soon as you ask for it, it's already available everywhere.
So let me backtrack a little bit. So basically what Nathan is saying is that once you ask in Bletchley, and nice going on reading the slides, that was awesome. When you ask in Bletchley, because I'm being asked about stuff that it doesn't matter. In Bletchley, we pre-generate a bunch of keys because the reality is that you ask Bletchley a key, why do you care if the key was generated right now or if it was generated a year ago? As long as it was inside of an HSM, it wasn't compromised and it wasn't used before, I really don't care. So we generate keys all the time. We have hosts that are basically their job is to generate keys, and they're generating keys, contributing to the pool. They get to a max. Okay, I have the key cache is full, cool. And then the consumers basically come around and ask for keys, and it's basically like a bucket, right? It's a leaky bucket. The keys are being taken out and people are generating keys back in, which means that if the bucket is really big, you can just sync them all and then have not of an issue with syncing, because if a key is produced right here, you still have 10,000 keys that can be used before this one actually has to be synced. So now instead of having to sync like in 200 milliseconds, you can sync Bletchley in a week, or you can sync Bletchley in 1 day, which is not really a distributed system problem. It just becomes, okay, I have to burn this DVD and go to my other data center and plug in this DVD.
We don't have to do that though.
We don't have to do that obviously, but it could be down to that.
Right.
It's a great question. 1 minute left. Actually, 59 seconds.
All right, thanks.
Thank you so much.